I have made several videos about this idea with two crystal filters in series to obtain lower phase noise at close range in an oscillator. Now this time I will go through it once again, looking for how to tune and design the different details. The basic idea behind this design is to use as much mismatch as possible of the crystal frequency to minimize noise outside the crystal resonance, and that is to get a low as possible flat noise floor from the oscillator. And the other problem is how to get the best close range sideband noise. It's a separate problem. First I will look at the second crystal filter, this here, and to do that I take the input signal, disconnect things here and route the signal to this point. And then I look here at the other side of the crystal, and I have disconnected here and look with the network analyzer directly on the crystal. Here is what I see. On the resonance the impedance is 70 ohms. Far away from the resonance I have 2.5 pf on one side and 11.5 pf on the other side. So it is capacitive, a fairly small capacitor, but it is capacitive, and I want it resistive. When I look through the filter, this is what I see with the same frequency span. It is 400 Hz over the entire screen. Now the frequency span is 10 kHz. I will add neutralization to get a more nicely looking filter response. I have changed this transformer. It's now 64 turns on the primary and 2 windings with 16 turns. It's a bifilar winding. And here is a neutralization capacitor that will neutralize the parasitic capacitance of the crystal. A special thing about FETs in grounded gate configuration, like here, is that the impedance looking into the source depends on the load on the drain. So first I have short-circuited from the drain up to this decoupling capacitor for a very low impedance on the drain. That minimizes the impedance on the source side, and I look at it with the network analyzer. And what I see is 10 ohms, nearly resistive. I have removed the short circuit here and instead put the resistor 3.3 kilo ohms from here to here, and then I will turn this capacitor up and down. I'm now making the capacitor larger. And that increases the capacitive component at the source. And if I go in the other direction, of course, it becomes inductive at the source. So this is how also reactive components go through the transistor. I have disconnected the 3.3 kilo ohm resistor that I had connected here. While it was in place, I had disconnected the second amplifier stage by cutting this connection. Now, when the resistor is removed, I have reconnected here, and I have removed the capacitor that was sitting here before. It made a very small difference. That was not important. The impedance I see on the sources of the first stage is 18 ohms, and that is probably a reasonable value to adapt, considering that the crystal is 70 ohms, so this is 25%. I'm losing a lot of signal, but the Q will be fairly high. I have reconnected the crystal here and disconnected here, and I'm looking at the impedance at the other side of this 780 pF capacitor, 680 plus 100. So I am looking at what impedance goes into these JFETs. This is not quite what I want. I want the highest impedance, this outside the crystal frequency. I want it as high as possible to minimize the gain of the amplifier. So I want these points move down here, and then the circuit should be centered to get as far as possible down at the point of resonance, which is opposite to that gap. I want the feed impedance feeding the sources of this transistor to be as high as possible. To that end, this inductor is tunable with an iron powder core or a brass slug, depending on what direction I want to go. And in the same way, I want to tune the impedance here. I tune it up and down with this capacitor. And I want to tune both of them for minimum flat noise. And to do that in a convenient way, I inject a weak carrier from the input here. So it comes here, goes through the crystal, and then I can use the noise sideband noise measurement tool of Linrod to tune for the optimum, because the carrier has a constant level, and these tunings do not affect the gain very much, just a little. I'm looking at the amplitude noise and phase noise at the same time. They should be equal in level, because this is uncorrelated noise, the flat noise floor. And indeed, it looks like they are very similar. And the level is minus 74.8 or something like that. I tune this capacitor half a turn, 1 turn towards greater capacitance. And I can clearly see a difference. It's more like 74.6 now. So I go in the other direction. First restore, and then 1 turn like that. This made a much bigger difference. So somewhere close to the original position, but just a little more capacitance than that should be optimum. Now this is pretty close to minus 75. Now I turn the iron core 2 turns inwards. Half, 1, 1.5, and 2. And I have to put the lid on to avoid interference from outside. Could be slightly better, but a very small difference. Well, I started by tuning this capacitor for minimum sideband noise. Means minimum noise floor, means minimum gain in this stage, or maximum impedance out from this capacitor. So that means that the gain is reduced in this stage, and therefore the sensitivity for also tuning this for highest impedance in this point is very a small effect now. I have expanded the scale to see better, minus 75.1, and I had to wait 5 minutes to get this kind of statistics. And I restored the original setting of the core, that is 4 turns inwards, and now I see 74.9. So in steps of 4 turns, I see 75.1 in the original position, and downwards is a little bit better. So I go one turn inwards from the original position, and I don't think I can see that difference, but it should be the optimum. Well, just a little below 75.1. So this should be the optimum tuning for lowest flat noise floor. The unit has been running overnight as an oscillator with a single crystal filter. And at 1 Hertz, I see something like 122.7 or so. So this is reasonably good for a single crystal, I think. At 10 Hertz, I see minus 156, but that is a bit uncertain. Maybe 1 decibel or perhaps 1.5 or so. At 500 Hertz, it's probably below minus 176. And I don't want to wait anymore, because the noise at a large distance should be the same also with 2 crystals, because I will not change anything in the amplifier when adding the first filter. Here are the numbers, and when I plot them, I find this line. And all the data points are within half a decibel or better, except for this one, which differs by nearly 1 decibel. But it was noisy, so it could be also on this line. And it's steeper than normal, and I don't know why. Now I am running the signal through the box, and this is the filter characteristic, magnitude and phase. So it's 0 phase at the peak, as should be. And I look for the bandwidth and Q. Q is 1.039, and the gain is 1.46 decibels. I will save this and then add the first filter and make sure that the gain at the peak is the same for the second filter and the amplifiers after it to operate at the same signal level as when it was just one filter. Here is the frequency response with both crystal filters. The previous, what I had, is here, and you can see it's twice the same curve, approximately. The phase is like this, and this is now, and this is the old one. So the phase slope is twice as steep, and that should give the frequency more precise and less noisy with phase noise, hopefully. And now the effective Q is 1.68 million and the loss 1.46. And I will turn this into an oscillator to see what happens. This is after 21 hours 45 minutes, quite some time. I have reasonably accurate readings, good statistics after such a long time. So 1 Hertz down here gives me minus 126.4 or so. I will take notes and compare with the old measurement. Here are the results. With 1 crystal, this numbers, dBc per Hertz. With 2 crystals here, and this is the difference. And it looks like 3.7 or 3.6 decibels in the close range, up to 3 Hertz or so. And then the difference goes down. But at 10 Hertz offset, the value is uncertain for the simple reason it's a bit noisy. And the difference between 2 noisy signals could be wrong by 1 or 2 decibels. so this could be 3.5 dB also. It would take a very long time to establish where the noise really is with the system that I have. The amplitude noise, the white track here, is well below the phase noise at frequencies below 2 Hz. And the correlation between amplitude modulation and phase modulation by noise is very small. So they have separate origins, the amplitude noise and the phase noise. The amplitude noise is very weak, only below about 1 Hz. I can really measure it. So these peaks could be noise. Well, this here looks like there's real amplitude modulation at 2.5 Hz. I don't know what that might be, but the amplitude of the pure noise is similar. Anyway, the amplitude noise in my test system is fairly high. It's about 128 dBc per Hertz here at 3.5 Hz. And the amplitude noise flattens out here at about minus 131 within this frequency range. The phase noise of my test system is more favorable. It steeps and it goes down all the way here, which is minus 138. So there is a lot of amplitude noise somewhere. I don't think it really matters, but it's something that I could look at. 3.5 dB gives me a curve, a straight line here. And I have seen better results than this, so something more than the number of crystals is at play. I have modified like this. Each transistor has 47 ohms and 0.33 microfarads to make the resistive component here not visible to the signal path. Resistors create noise, but not with this capacitor in parallel. I also discovered that this resistor, which has been 14 ohms according to the schematic diagram, actually was 27 ohms. So the current is similar here as here now. My idea is that the oscillator is a system with positive feedback, maybe very close to the frequency of oscillation. The flicker noise from the transistors could get amplified. So there would be some effect here. But if that doesn't happen, there should be a difference at 10 Hz or maybe even a little bit earlier. At 5 Hz, this distance is 8 decibels. That's a factor of 6. So 1/6 of the noise I have comes from the flicker noise, which should be this curve, when the transistor had the same current. Rather, they had the same source resistor. And down here, there should be a 3 dB improvement. I didn't measure at 14 Hz. I cannot do that now. It would take a very long time, and I'm not sure if that would be reliable. Here is the screen after nearly 2 hours. I can see there is not much difference. At 0.5 Hz, I can read 115.7. It was 116.0, and that's within the uncertainty. At 1 Hz now, 126.4. That's exactly what I had before. 1.5 Hz, 132.3 or so. That's exactly the same. 2 Hertz, I would place it 137.0. It was 136.5. And 3 Hertz, 142.5 perhaps. It was 142.4. The conclusion is there is no difference at all at close spacing. At 5 Hertz the noise is fairly high, but it looks like minus 151. And previously I had 149.4. And 10 Hertz, it's in the noise and I cannot read anything reasonable here. I had 157.5. That's down here. And that's in the noise, so I cannot say anything about it. Anyway, I don't see any advantage of having separate currents for the different transistors in the first stage. Probably there is a difference at wider offsets, maybe 20 Hertz or so, but that's outside what I can measure with my current system in a reasonable averaging time. I have now connected I of RF channel 1 to channel 1 of the sound card, nothing to channel 2 of the sound card, and the Q channel of channel 1 on the RF side to channel 3 of the sound card, and nothing to channel 4. And then I look at the correlation spectra, and here I can see very clearly that the phase noise up to about 3 Hertz is the same in the sound card channel 1 and 3, but at higher offsets they are different. It means that up to this point the noise I see comes from the reference oscillator I'm using, but above that the noise has some other origin. The amplitude noise is very different. As you can see, the imaginary part is similar to the real part. So the correlated noise between I and Q is very low, far below the actual noise, means the noise doesn't come from the oscillator, maybe from the mixer, maybe from somewhere else. It could be interesting to try to find out where. I have connected the same signal to channels 1 and channel 3 of the sound card. And then phase noise looks like this. At offsets below, say 1.5 Hertz here, we can see that the noise is the same in both channels, and the correlated noise is the same as the noise in those two channels. But as frequency offset increases at 4 Hertz, it's obvious that the correlated noise is well below the noise in the two channels. It means that this noise originates in the sound card, while the noise on the signal is down here somewhere. And this is the phase noise. The sound card, UADC4, uses the AK5574 A to D converter. It's a 4-channel chip. Channel 1 and 2 uses one reference, this one, while channel 3 and 4 uses another ref. It's this one. I was thinking perhaps there is uncorrelated noise on these reference inputs, so I have put the wire from here, ref 1, to here, reference 2. Because if there is noise, there will be the same noise on the reference voltage for both stereo channels, means 1 and 2 and 3 and 4. They would all share the same reference voltage. I am still sending the same signal into channel 1 and channel 3 and nothing into channels 2 and 4. Then I get this curve. The noise is the same in both channel 1 and channel 3, down to a level of about minus 134 dBc per hertz, which happens at about 3 hertz offset. And then the noise is constant, while the correlated noise goes down. So this means that this is the phase noise of the AD converter itself, and it's different between the channels 1, 2 and channels 3, 4. The amplitude noise is much stronger. Up here, the phase noise was down here somewhere, but it's uncorrelated between channel 1 and channel 3. So the correlated noise is down here, or rather below somewhere, because the imaginary part, the red dots, are equally strong as the white trace. So this is a property of the AD converter. I cannot do anything to improve on that, I think. The signal level now is 3.66 volts into 50 ohms. That is 33 milliwatts. This is the amplitude limiting at the moment. 3 parallel 1N, 41, 48 in each direction. I have changed the limiter like this. It would now give twice as much voltage, roughly, to the input for about 6 decibels more power output. And here is the output, 7.65 volts. That's 146 milliwatts, and that's into 50 ohms. With about 6 decibels more power output and also 6 decibels more power through the crystals, the phase noise is much higher. At half an hertz before it was minus 116, now it is minus 113. That is 3 decibels. And here at 1 hertz it is now minus 122, and before it was minus 126.4. That's 4 decibels. 1.5, I have now 128.5, and it was before 132.3. So this is significantly higher. I will save this screenshot. I have inserted a 6 dB attenuator at the output of the oscillator. That is to isolate it from my 2-channel receiver, because I know that the frequency of the oscillator is very sensitive to variations in the load impedance. So this is just a test to make sure that there will be no difference. And here is the curve I have now. And here is the image I saved without that attenuator. And it's 1 dB per division vertically. So the curves don't differ by more than 1 dB. So that is not one of the problems I have. A higher power level into the crystals was obviously not a good idea. So now I have put Schottky diodes instead of the 1N4148 to get a lower clipping level. The output level is then 1.72 volts into 50 ohms. That's about 7.4 milliwatts only. The phase noise is significantly lower. at 0.5 Hertz, 115.6 or so, and 1 Hertz, 126.4, and so on. I will take down the numbers. I have been running for 9.5 hours only. The values at close range are very similar to what I had with the 1N4148, but at larger separations, 3 Hz and above, I get a gradually increasing loss. That is probably because of the short time, but it could also be because I am approaching the flat noise floor, although I don't think so. Anyway, I don't want to run at this low power, so I will restore, at least for now, the 1N4148 diodes. I have restored the amplitude limiter 3 times 1N4148, and the power is back at 33 milliwatts on the output. And that's of course 3.66 volts. I will inject the signal from my signal generator to get the same power output. The power I need for that is 8 dBm according to this generator. I am doing this because I want to know the load on the crystals. So what you see here, 55 millivolts peak to peak, is on the sources of the 6 JFETs. And here is the emitter of the dipolar for the first crystal, 30 millivolts. Here is the impedance on the sources of the JFET. It's about 17 ohms off resonance. Here is the emitter of the BF240, about 6.7 ohms off resonance. And it's very small difference on the resonance. The current is now similar in both crystals. Here, as well as here, the current is about 2 milliamps. This resistor, which was previously 120 ohms in the schematic diagram, was actually 470 ohms, and that's not enough current. So this transistor got saturated at the higher signal levels. I have now put 270 ohms here, and that is close to the point of saturation at this crystal current. The output power is 120 milliwatts, and I have put two 1N4148 in series with 2 Schottky diodes, BAT42. And that's why the output power is relatively high. I will see whether this is still low noise design or something wrong might have happened. Already after 1.5 hours, I can see this is not quite what I wanted. This is 1.5 Hertz. Before I had minus 132.3, that's where the mouse is. It's more than 3 decibels degraded now. At 2 Hertz, I had minus 136.5. That's here. That's 3 Hertz. At 1 Hertz, that's here. I had 126.4. That's here. So this is not really what I want. I will return to the original limiter with 1N4148, 3 of them in parallel. Now close range performance is restored, as expected. Previously I had 116.0 and 126.4 at 0.5 and 1 Hertz. And that's very close to what I can read here. Now the unit has been running for 33 hours and 49 minutes. So I have a stable result. And at 0.5 Hertz I can read minus 116.4 perhaps. And at 1 Hertz 126.0. And then if I go out to as much as 4 Hertz here, that is minus 145.5. That is about 1 decibel worse than I had before. So I will take down all the numbers and compare. I can get a reasonable reading up to 10 Hertz offset. Here at minus 156. The imaginary part is in this interval, and this is 4 or 5 dB above the extreme values, or from here to here is enough to get a fairly accurate reading. 156.0 plus minus something, of course. But 20 Hertz, this is in the noise, and I cannot say for sure where. At larger offsets, the correlation gain is not high enough, and I don't want to wait a couple of days to see, because I'm not sure I can trust whatever result I would get. It seems I have made a mistake now, because at 0.5 Hertz there is a small improvement, but at larger separations there is a gradually increasing loss of performance. 1.5 dB at 10 Hertz and growing continuously. So this is a significant observation, not large, but in the wrong direction. I realized that I made some mistakes here. I measured the impedance of this transistor, but it was a bit saturated, so it could have been higher when I was measuring the voltage than it was when I was measuring the impedance with the network analyzer. After that I has changed a resistor, not this one as I told you just recently in this video. It is this one, 470 ohms, that I have changed to 270. And this is still 470. So I will check these things. The impedance at the FETs, I don't think that changes at the drive levels I am running now, but I will check that also. I have temporarily restored 470 ohms here, and then I measure the impedance on the emitter while the oscillator is running with full amplitude on the oscillations. On the screen it looks a bit ugly, but if I look at the marker, I'm at one end, I'm spanning 10 kilohertz, so this is 5 kilohertz away, and then I change the frequency all the way through, and then I see about 6.7 ohms, and at the other end it's also 6.7 ohm. And that was what I found before. So there is no change, no saturation at this power level. I still have the same nominal output at 8 dBm input into the filter amplifier box. I have increased by 6 decibels to 14 dBm, and now I see clearly a significant heating of the crystal. And I can see that there is an hysteresis when I step frequency upwards or downwards. Here is the waveform on the emitter when the input is 14 dBm, 6 decibels above the normal oscillation level. And the waveform is pretty ugly. With 270 ohms, this is what it looks like. The impedance then is 4.33 ohms resistive and 3 ohms inductive. In total that makes 5.3 ohms. The level on the emitter is 19.5 millivolts at 8 dBm input power. 6.9 millivolts, 5.3 ohms becomes 1.3 milliamps through this crystal. And here 20 millivolts RMS, 17 ohms, 1.18 milliamps. So the currents are very similar. And before, the current was significantly larger in the first crystal than in the second one. So what to draw as a conclusion of that, I cannot say. This has made no difference. There is still about a 1 dB loss. At 4 Hz I should have 146.5. That's down here. So it's even more, it's 1.5 dB as compared to what I had when it was at the best. Now I notice something. If I go close, there are some things happening also here, and I can see it even stretching out here. This looks like a connector problem. I will clean the BNC connectors once again. I have flattened one of these tops, they are called, I think, and then I clean connectors like this, and it looks like this. Means it wasn't clean enough, so this could have been a problem. Once more, using the other side of this cotton stick, I'm using isopropylic alcohol to wet the cotton. And the next one. And this black stuff, I guess it's just small metal particles. And the same for the male connector. This is a gold-plated pin. And you see it has this black stuff on it also. And finally the ground connection. And finally the center connector. This brush is well wet with the isopropylic alcohol. Something has gone wrong with my oscillator. Here is an event with asymmetric noise, more on the low frequency side. This means that there is amplitude modulation as well as phase modulation at the same time. When I look here in the diagram where I have the correlation between the modulations, I can see that at an offset of 1 Hz I have a strong correlation between AM and phase modulation. And AM and phase modulation are in phase. It's the white trace that is almost 1. It's 75% approximately. And the levels are not catastrophically low, but at 1 Hz the phase noise is at minus 115. And the amplitude noise is at the same level. And normally amplitude noise should be much lower than phase noise, but not so here. So there is some new phenomenon that happened. And at the moment I'm running with the Schottky diodes to limit the amplitude. So this is a low amplitude oscillation with some poor connection due to a bad soldering or something else. I don't know what the problem really is, but the problem is here. I'm trying the brute force method of repair. It's immediately clear that the brutal force has improved. That is where I used the hammer, and now the signal is narrower in the main waterfall. And it's also clear from the baseband waterfall, it was asymmetric before and rather wide. Now it is much narrower and it looks symmetric. And if I look at the noise, the sideband noise spectra, I find that the AM noise is down here, while the phase noise is something like that. And I don't see any correlation. And that's natural because the amplitude noise is not significant yet. It will take quite some time. Here is the phase noise after 6 averages only. It looks like something like that, which is compatible with -116, which is what I should expect. And at 4 kHz, I wanted to have it at 146.5. That's down here. Maybe, maybe not. The amplitude noise is not significant yet. It is blue and white. Blue means negative, means undetermined. The imaginary part, the red dots, go up to here and down to here, and they are of the same magnitude as the real part. So this doesn't show any amplitude noise yet, and it's only 9 averages so far. And I will have to wait, and maybe that instability problem will come back, or maybe it will stay away for some while. The baseband waterfall looks okay now anyway. We'll see how long that will last. The brute force repair seems to have been successful for about 20 minutes now. And the phase noise looks okay. -116 here and -126 here. And at 4 kHz I want 146.5. It's down here. It's maybe a little questionable. The brute force repair lasted about 1 hour, from here to here. And now I have this extra noise, and it starts to increase up here. I don't know where this comes from, and it's very hard to find out. It could be a bad soldering. I have seen such things in the past. But there are many solderings in the box, and they all look a little bit ugly. I will try to heat up everything and see if that helps. It could also be a problem with the crystals, although I don't think that is likely. Reheating almost all soldering joints in the unit has not helped. Finding the intermittent source, like this that I have now, could be very difficult in a fairly complicated unit like this one. But there is a method to do a systematical investigation, and that is to use the interferometer. That means I will inject the signal here directly to this point where all the 10 nanofarad capacitors go into the JFETs. Here is what I see after almost 1 hour. In the baseband waterfall I see no irregularities. and also not here. And I get a phase noise spectrum that I can read out here. The carrier suppression is 50 decibels. So at 0.5 Hertz, the first line, I read minus 96, means minus 146. And so on. I will take down the numbers. By compressing the x-axis, I get a little bit better statistics. So I can see at 4 Hertz offset, it's about minus 161. This is what I got for the second stage. After having done the measurement, I found that I didn't set the level properly. So this line is about 2.5 dB too high. And it's in a good agreement with what I found before for the second stage. That is this line. So everything is okay with that part of the box. I have disconnected the crystal here and here also. And I'm feeding the 6 JFETs through a 4.7 PF capacitor to feed from a very high impedance, as is the usual procedure off resonance. I observe 147.5 at 3 Hertz. That is about here. And that's high above the previous results I had. So I have to find out what did I do wrong. I haven't seen any instabilities, which is what I'm really hunting for, but the higher noise floor is not acceptable. When I gave the FETs separate source resistors, I increased the current in order to get a lower impedance, to get a higher loaded Q for the crystal. Maybe that wasn't a very clever decision, so I will investigate that. Indeed, when I put 22 ohms in series in this point, that's equivalent to give the transistors 132 ohms each. Then the noise goes down from 147.5 to minus 152 at 3 Hertz. So the very high current is not good for the noise properties. I have set parameters in Linrad to get fairly accurate readings within half an hour. So, for example, here I can see 88.4 perhaps, 93.1 maybe. So, accuracy plus minus 0.25 dB or so. I have been trying different values for R1 and R2 here. And then I get these results. R1, R2, the effective resistance to put if everything was only R1s. And then source voltage and current. And the phase noise at different frequency offsets, 4 frequencies, and the sum over all frequencies, and then the difference between the sums divided by 4, which means the average difference between the different noise spectra. And it's obvious, as the current through the transistor is decreased, the noise is improved by as much as 5.5 dB, from 17 milliamps down to 5 milliamps. Now, at the same time, the impedance that the crystal will look into is going to be higher as the current is lower. So I will measure the impedance for the input into here for the different cases to see what I think will be the optimum compromise between noise and the Q for the crystal. And then when I move all the resistance to R1, the transistors will have separate currents, so that should make a small improvement on top of what I find from this table. The impedance on the sources turns out to be 16 ohms at a current of 17 milliamps, and it increases up to 20.7 for a current of 3.5 milliamp. This impedance depends on the load on the drain as well as on the current, and it doesn't seem to be too bad, so I tried a bigger resistor to see what is the noise here at only 3.5 milliamp current. I think this could be the equivalent schematic diagram of the crystal filter. 70 ohms is what I measure when measuring towards the crystal, and this is what I just now found is the input impedance of the amplifier. I think Q has to be proportional to a constant times 1 over R, where R is 70 plus whatever ZS is. I'm not sure on this, but this is a reasonable guess, I think. I have the resistances 16 up to 21 ohms, and I want to see what happens to Q. So if I say Q is K times 1 over R, I can compute K by guessing that the original configuration had a Q of 1 million. And that gives me that the K is 86 million, and that gives me that the Q with the largest resistor is 86 over 90 times 1 million, which is 950,000. And I think this can be tolerated, because there is another crystal filter also, so losing a little bit on the Q on one of the crystals shouldn't be that terrible. As it turns out, it is not so critical. I had the best result here at 5.4 milliamps. Going down to 3.5 degrades, but very little. And going up to 8 degrades also, and a little bit more. But on the other hand, the Q is going to be a little bit higher. So somewhere between 311 and 179 ohms is what I want. And I think I will select 270 ohms when I put all the resistance here and nothing here. As it turns out, the advantage of having separate source resistors is very small. With the 270 ohm for all sources, I get 5.98 as the average improvement over the original 47 ohms. And that's just half a dB better than what I had with one resistor for all the currents. That was with 311, but 207 is pretty close. So it is not an essential thing to do it like this. Here is the interferometric result after 8 hours with 50 decibels of carrier suppression. It means that the flat noise floor is around here. That's minus 178 dBc per hertz. The phase noise I now see with the interferometer coincides almost exactly with the old line I measured before, but only from 1 Hz up to 10 Hz. At very close range there is a large discrepancy, maybe because this time I had only 50 decibels carrier suppression, so there is some noise from the Wenzel generator leaking through. Or maybe something else with the settings of Linrad I don't really remember. But these points are very accurate, the same. But at wider offsets, the noise is much higher. And it seems that the flat noise floor is something like 12 decibels higher or so. The signal level has been 2.26 volts peak to peak, and that's 12.7 milliwatts, and it's into 50 ohms. I have shorted the crystals with a wire from here to here and another wire from here to here. That's in order to measure this stage and the transformer. I had to add 5 pf across this capacitor as well as across this capacitor to get a reasonable signal level. Still significantly lower than before, but a signal that I can easily measure what happens on it. And I'm looking for the intermittent noise bursts. And here is what I see. These numbers don't differ much from what I saw from the rest of the amplifier without that first stage. And here there are no really significant intermittent problems. The noise has been a little bit larger here and a little bit smaller and then a little bit larger. And that could be because of the stability in the interferometer. The carrier goes up and down by maybe as much as 1 decibel. I haven't been looking at it during all this time. It's 4.5 hours. But right now the level is a little bit lower than it should be. So the noise should be a little bit lower than it was when I started the measurement. So this is due to temperature variations in the room here. 50 decibels of suppression is quite a bit. The loss of performance from here to here is nearly 2 decibels. And that's very small, and I see no intermittent pulses of noise. So the problem is elsewhere. I have again converted the box to an oscillator with a single crystal, with a wire from here to here and a short to ground from here. I have measured the phase noise during many hours at different power levels. I can set the power level by changing the diodes of the amplitude limiter without changing anything else. What you see here is at 112 milliwatts output power. And I take down the numbers in a table like this. And here it's obvious that going for a high power, that was 200 milliwatts. The noise levels are significantly degraded, 126, while at very low power, that's 11 milliwatts, it was minus 129. So it's about 3 decibels degradation at this power. Then the frequency is different. At low power it is 953.246 Hertz, offset from 9999 kilohertz. And at high power here it is 959.238. That's a difference of 6 Hertz. So it must be heating of the crystal. So those 3 decibels of performance loss could be due to the temperature or due to something else that I don't know about. Then at half that power, 112, I still have a performance loss, half a dB from here to, 1 dB to the very low power, but half a dB to the decent power of 50 milliwatts. Anyway, this shows that too high power heats the crystal and causes a significant performance loss. So this sets the power level for this crystal. During these tests, in the very first test, I saw a single burst of noise. Not burst, it was a high noise level, which I repaired with a single stroke with the hammer. And since then, during many hours, I haven't seen one single burst of noise. So it could have been the crystal that had some peculiarities. I have seen such things from standard crystals many times in the past. These fundamental 10 MHz crystals typically behave like that when they are new. So some aging fixes it. This one is not new at all, but it had been switched off for quite some time and then was restarted. Now that I know the optimum signal level for this crystal, I have grounded on both sides of it to eliminate it from the circuit for a while, and then I get the same amplitude and phase in this point with this RC link. This is 1 nanofarad. And then when I apply feedback without changing anything at all, I get the same signal level as I had before, and I will look at the noise that I have from this crystal filter and then see whether it behaves in the same way when I increase or decrease the signal level through this crystal. And at the same time, of course, I will look for those intermittent noise events that I don't know from where they came. I'm happy they are not there anymore when running this crystal, but now I'm running that crystal. We will see. Here is what I have. This is many hours, from 6 up to 14, 8 hours running with the second crystal filter. And here I made a little change, and here it is running with the first crystal filter. And as you can see, there was a short period here when it was okay, but now it is noisy. I will try a quick fix, the brute force thing. Just one knock on it, and then I have to wait for a while because Linrod is slow. This was not good at all, as you can see in the main waterfall. It's really noisy now. And in the baseband waterfall here, you can see it's not blue, it is dark red all the way out on both sides and very much white in the middle. So I have destroyed the oscillator more or less completely. I give it another try. Better luck this time, as you can see already in the main waterfall. I must say also that the crystals are in a heavy piece of metal for temperature stability. It's a brass thing which they are placed in, heavy, and that brass thing is placed on in a compartment filled with foam plastic, so it is well isolated from vibrations, because it should be well isolated from temperature variations on the outside, and it should have a thermal time constant to stabilize and make the same temperature for both crystals. So that hammer did not reach the crystals directly, but well damped the vibrations are. And it takes some time before I can see if it is better or the same or worse. The noise level is high, particularly at 0.5 Hz, where it is minus 108.5. And the table I make, very high noise here, and pretty high here, 120.5. I could see that at the maximum power for the second crystal. and then it becomes a little bit better, but it's still not so good. So I will reduce power on this crystal to see if the frequency changes because it is now a little bit overloaded, or if this stays the same, which means the crystal is not as good. I have measured the phase noise at 7 different offsets from 0.5 Hz to 5 Hz. And then I have taken the sum of all of them, and the average is down here. And at different power levels, for the second crystal filter at different voltages, comes at these powers, 51 milliwatts up to 205 milliwatts, and down also to a very low level, 11 milliwatts. And the average noise I can see, this is good, even better than what I observe, well, the same as I see with much lower drive level. So about 50 milliwatts output, that's the level I want to drive the crystal at. Of course, the power in the crystal is something completely different, but I reference to the output level I see, and I have to be careful if I change something in the amplifier. I can use this information to make the design so the crystals operate at the optimum power level, and not very unexpectedly it turns out to be similar in both filters. The input circuitry on the filters is the same, so I should expect them to want the same drive level. The load on the output side, whether it is 4 ohms or 17 ohms, doesn't make much of a difference on the load of the crystal, because most of the power is dissipated in the crystal and very little in the load, because the load is in a strong mismatch to the crystal impedance to get a very high loaded Q for the filter. This is how I understand the crystal filter. The inductor, that's the crystal. The load impedance, that's the input to the amplifier. 4 ohms for the first crystal, or 17 ohms or something like that for the second. And then this is the input impedance. That is 25 ohms for the first, and at the moment it's 100 ohms for the second filter. I will try different source impedances. I can put a resistor in parallel to make a lower impedance, or I can put a resistor in series to make a higher one. And to see that I don't have a possibility to gain much by changing it towards lower values, because the lower I make it, the smaller losses it will introduce into the main resonator, which is capacitor inductor. And the losses into the amplifier, they are unavoidable. Parallel resistors on the first stage, starting with 3 ohms, gives a Q of 1.165 million. And then I try no resistor at all. Then I have 25 ohms, because there is 50 ohms from the generator and 50 ohms as a termination resistor in the box. That gives a Q that is slightly lower, but not much. The ratio between ideal and what I have is 98.5%. And then I try to load it, and I gain a little, and load it further. It becomes slightly better. But these are small improvements, and there is a big loss of gain. I could drive the box to give 6 decibels more output, and then I could turn the coupling capacitor to become smaller to get the same gain. That could give a small improvement on the Q of the first stage. The second stage, I put 3 ohms in parallel, and then I get a Q of 1.107 million. And then I use instead series resistors. That means no series resistor gives me a Q of 989,000. And with 47 ohms in series to give me 97 ohms, that's the source impedance I have now. That gives a Q of 969,000, and that is 95.2% of the optimum Q I could have on the second stage. So I will try to improve here. If I can make the source resistor smaller, bringing more power from the first amplifier stage, I could reduce the coupling capacitor. I will look into this a little bit. I have decided to go for 4.5 volts peak to peak on the output. That gives me 9.1 dBm for the feedback. The output is then 50 milliwatts or plus 17 dBm. When I inject 9.1 dBm on the input and make sure I'm at the center of the crystal, then the voltage in this point is 0.92 peak to peak, and the saturation, if I disconnect this 100 ohm resistor, is at 5.7 volts. This means that I should reduce the number of turns here by a factor of 2 probably. That would give twice as much current this way, so I could reduce this capacitor by a factor of 2, or I could reduce this resistor down to 50 ohms. And I think it doesn't matter which way I go. And maybe I could even reduce the number of turns further. But I want to stay away from saturation reasonably far. It happens at 5.7 volts on this point when there is no resistor here. There were some problems with oscillations around 800 MHz. So I have added 4.7 PF in series with 100 ohms on both emitters as well as on the common collector. And that kills oscillations efficiently. Here is the frequency response through the 2 filters. That's through the entire box. So gain is 1.5 decibels, and the phase at the peak where the cursor is 0 degrees, as should be. And if I look for the bandwidth, it tells me that the Q is 1.72 million. That's the combined Q of 2 filters, and what that does to the oscillator noise, I don't know yet, but we will see. There is an instability. I don't know where it comes from. It could be the fuse. I have here a fuse because there are very big capacitors that supply the 16 volts to the unit, and shorting them gives a current peak that things become destroyed from. So this fuse protects me from bad problems when I happen to short circuit something. This is 18.5 hours. I don't have any intermittent noise in the baseband waterfall. It looks fine. And the sideband noise is now stable enough so I can read values 116.5 at 0.5 Hertz, and maybe 126.5 at 1 Hertz, and so on. The results I get with both filters is in this column. And if I compare with the best one of this and that, the improvement is about like this. 3 decibels up to 1.5 hertz, and then above 3 hertz, very small, and at 5 hertz, half a dB, and then probably nothing. Now the bandwidth of the combined two filters, the 3 dB point is plus minus 3 hertz. So it's not surprising that going well above 3 hertz, there is no improvement anymore, because the noise comes from the second crystal and it doesn't pass well through the feedback system. But very close to the carrier there is a 3 dB improvement, because the frequency is determined by the phase rather than by the amplitude through the filter. And the phase slope is twice as high with the two filters. And that gives a factor of 2 in suppression of noise, because it's the uncertainty in the phase that determines the frequency of oscillation. Well, that's my theory for what I am observing. Probably this is well known to experts in the field, but I'm not an expert. I'm just doing what I think is interesting to me. The frequency indicated has the decimals 958,973. This means that the 50 Hz mains should appear at 8.9 Hz from the carrier. And that's the signal we can see here. In channel 1 it's pretty strong, in channel 2 it is very weak. And it has been here and also down here, because nowadays with wind power the mains frequency isn't very stable anymore. So the region from 5 to, well, 6 or so up to 10 Hz, I have no good reading for that. And when I compress the X scale, I can read minus 155 for 10 Hz and let's say 161.5 at 20 Hz. But that's fairly uncertain, and the imaginary part goes from here up to here. When I compress the frequency scale further, it's obvious I have a big problem in this range. That is this signal on one side, together with the third harmonic here. They present something that looks like sideband to the real signal here. So this region is more or less useless. But above, let's say 200 Hz, the measurement should be okay, but signal to noise ratio is absolutely not good enough yet. And still it is 23 hours now. I could read reasonably well the values at 10 Hz and 20 Hz. Then I made guesses for 200 up to 500 Hz based on the curve that looks like this. I will allow it to run another 24 hours to see whether this has changed significantly. After 47 hours, and with a strong compression of the frequency axis, I can see that the noise floor, the phase noise, flattens out at minus 177 dBc per Hertz. And then how it goes here, I'm a little bit uncertain, but the scale is only 2 decibels per division. The amplitude noise is similar. It seems to flatten out at minus 180 or so. The system is not quite as good for amplitude noise, so the distance from here down to here is bigger than it was for the phase noise. Amplitude noise and phase noise in the same diagram shows that they are very similar. And correlation between them seems indeterminate because there is a big random component in the measurements. The signal-to-noise ratio of the correlation spectrum is not very good. Although this is 47 hours, quite a long time. Looking at close range from 1 Hz and up to 14, I can see that at very low offsets there is no correlation, and with increasing offsets the noise increases. I cannot say much about this. I don't have good enough equipment, obviously. With more than twice as long time, I get a smoother curve and I can read the phase noise with a little better precision than before. 0.5 Hz, 1 Hz, 1.5, 2. So it compares to the previous readings pretty well. Half a dB better here, the same. Half a dB better here, the same. Half a dB better, and half a dB better. Here is what I can see after 48 hours. The lines, this one and that one, have the appropriate slope for B-1 and B-3 with these values. The data points up here and this deviate from the line significantly. This could be because of noise on the power supply. The power supply has an RC filter, 20 ohms and 450,000 microfarads. That's a time constant of 9 seconds. And 0.2 Hertz, that's 5 seconds. So maybe there is some supply noise. The unit is very sensitive to the voltage because the drain source capacitance of the FETs varies with the voltage. So a good supply stabilization is required for this design. Here are the parameters I have been using for this measurement. I have increased the baseband sampling rate by a factor of 8. So now I can see up to 4.5 kHz offset, and it looks like I'm approaching the flat noise floor with minus 183 decibels here. I can look at the amplitude noise, which at the flat noise floor should be the same, but it seems to be at about minus 184. So maybe if I had a wider range to look at, I should see the white floor at minus 184. From that I get these 4 points. They are not so accurate, but they fit well, and I guess the white floor is at minus 184 down here, based on what I saw on the amplitude noise. That means B0 minus 184, B minus 1 minus 151. It's this point where this line crosses 1 Hertz. And B minus 3 minus 127. This is the slope for B minus 2, and I don't think I can find any of that. So that is an improvement I made. But the flat noise floor, minus 184, I have seen better before. Here are the parameters I have been using for the wider bandwidth. Actually, it was possible to increase the baseband sampling speed by another factor of 2. So now I can see up to 9 kHz, and here the level is minus 183.5. If I zoom out like this and go for the amplitude noise, you can see it goes down to minus 184, and it doesn't slope here. It's more or less flat, but it's more noisy than the phase noise, and that is because the uncorrelated data is higher here for the amplitude noise than it is for the phase noise. When I look at both at the same time, like this, I can see the yellow is above the white, but I can see here, I can see clearly a correlation that grows with offset. Whether that is a problem with my measurement system or whether it is a real phenomenon in this oscillator, I don't know. I have increased the level by 4 decibels by changing the amplitude limiter. And as you have seen, it goes rapidly downwards. But I will have to wait some hours to see where it stabilizes. Already now, after 20 seconds, it's down at minus 178. With a 4 dB stronger signal, I should expect the white noise floor to be 4 dB lower. But that's not what I see. The cursor is at minus 185 here. This is only 1 or 2 dB better than before. And I can look at the amplitude noise, and it's about 1 decibel below the phase noise. So it's also higher than expected. Now, there could be 2 explanations for this. This could be a property of my test system. For example, I can imagine that very high overtones of the 41 Hz audio have very wide noise spectra on their sides, so they could arrive here somewhere. But it could also be that the noise floor of my oscillator rises when the power level from it increases. Here I'm using the 2 SDR-IP units. They are locked to my 2 10 MHz reference oscillators, which are locked to each other but with a very long time constant. Anyway, this is useless, as you can see. There are various spurs in the SDR-IPs. Here is a strong one, for example. It gives a peak here in the correlated spectrum. But there are various peaks, many of them, and they are at a level of about minus 176. Minus 184 is in the middle of this. So I cannot measure the phase noise with this system either. As expected, the higher power gives a degraded close-range performance for the phase noise. I will take down the numbers I have here after 9 hours and a half. The elevated power, just 4 dB more, gives a curve like that. It has a steeper slope because these points are identical. And the loss at 0.5 Hz is about 3 decibels, or maybe even 4. I don't remember exactly, but these are the points. And this is not what I want, so I will revert to the previous configuration. The signal level has been 7.05 volts, peak to peak, and that's about 125 milliwatts. I have set the Linrad S-meter graph to show 0 for the carrier in channel 1 with the 4.5 volts output from the oscillator. I have connected this signal generator to the feedback input and also terminated the feedback output in 50 ohms to have the same load on the output amplifier. And then I set this level, so I read minus 100 decibels here. So the signal is now 100 decibels weaker than before. I have increased the gain of my 2-channel receiver by 23 decibels, and now I can easily see the noise floor, the correlated noise floor, the green trace you can see here. And I can change the correlation mode so I get out the AM and the FM noise with this 100 dB reduced carrier level. This now very fast gives me the noise floor at minus 84.5 dB, or maybe minus 84.3 or something like that. And this is the phase noise. I expect the amplitude noise to be exactly at the same level. Of course it is, because this is white noise from the amplifier. Well, after 5 minutes I see 84.5, and this is AM noise and FM noise at the same time, and there is no difference between the curves. And the correlation between AM noise and phase noise is 0, as it should be, except on the spur that I have here, of course. With the carrier at 50 milliwatts plus 17 dBm, I find the flat noise floor, AM noise as well as phase noise, at minus 184.5 dBc per hertz. Pretty good agreement with the B0 I found from measuring on the full signal when the oscillator was running as an oscillator. Now the total noise then is 3 dB higher. AM and phase noise add with 3 dB because they are uncorrelated. That tells me that the noise floor is minus 164.5 dBm per hertz. This is the Linrad screen when I'm looking at the signal from the oscillator, which is not running as an oscillator but just as an amplifier with 50 ohm terminations in the 2 feedback ports, output and input. I have set a very high resolution. The bandwidth of the main spectrum is 0.1 Hertz. The green trace is the average of 7,000 correlation spectra, while the yellow is the average of 61 spectra only. And that is also the white, which is the normal power spectrum without any correlation. And I can read the level of the white trace, the normal spectrum, here, and it says 1 decibel per hertz. And it is within a bandwidth from the baseband here of about 2 hertz. And to that comes a correlation advantage, which is about 0.4 hertz. The white trace and the green trace, they are almost on top of each other. I'm running in SSB mode, which means that the frequency indication that I read here as 10.00000, that is the frequency of the beat oscillator, which I have placed at a suitable distance, about 41 Hertz above the passband. And then the box here has a T, which means tune. So I can tune about 3 Hertz away. That is 1, 2, 3, something like that. And this was 3.1 Hertz, so I used the mouse wheel to bring this down to 3,0,0,0,0. And then I have to wait quite some time to get the readings from this new frequency. I get the correlation advantage immediately, but I have to wait for a while for the evaluation from the baseband that I get here in the S-meter graph. You can see the level is a trifle lower. Looks like 2.5 decibel or so. But I will have to wait for this. Statistics is very slow because of the very narrow bandwidth of 0.2 Hz only. Here is the level at plus 3 Hz offset, minus 0.97. And the correlation advantage, it says 0.33. And that is the statistical phenomenon. As you can see, it happens to be a low point in the white trace. And I cannot make the white trace better than this because with the current settings I cannot have more than 61 averages. So if I wait for a while, this is going to grow up to maybe 0.4, 0.5 or so. So the decimals don't mean anything. I take this as 0.4 also. Next I have a look at 3 Hz on the other side of the peak. And I have to wait for the new reading, which should be very similar. 3 Hz on the low side means 0.997 here. Gives me a noise floor of minus 1 dB per Hertz. And the correlation advantage is 0.66. So this is the same within the accuracy I have. At an offset of 20 Hz, where the correlated spectrum has a less steep slope here, I have set the bandwidth to 5 Hz. That gives better statistics on the evaluation of the noise level, as well as of the correlation advantage, 7.0 here, and whatever it was down here, 7.4. So I will continue to evaluate on both sides, and it's clear that here the correlation advantage is quite big, and at the corresponding level here it is much smaller, because here I don't have the noise increasing towards the DC level for the sound card. Here are the parameters I have been using. And note that the first FFT bandwidth, as you can see here, it states 10, but if I go for the parameter menu, you see it is a factor of 100 bigger in the parameter table, so the bandwidth has been 0.1 Hz. And I will increase this to 10 Hz now to get a wider range and a faster response. Calibration is different with these different parameters for the first FFT. So I read 4 dB per Hertz when I measure the frequency, the center frequency 10.00. And the correlation advantage says 0.25, 0.3. That is similar as before, should be the same actually. And it is the same, 0.4. And it varies a little with time. So now I can use this and then measure at wider separations. I have measured the noise at both sides of the peak caused by the crystal filter. 0, that's on the peak, and plus 3 Hz, minus 3 Hz, minus 6, plus 6, and so on, up to plus minus 2 kilohertz. And it's an uncorrelated value and the correlation value that comes to it. And it's very different on the two sides. for example 15 Hertz, the correlation is 5 dB upwards towards the zero frequency, but 3 decibels downwards. And at 30 Hertz the difference is even bigger. But the total doesn't differ that much. Probably the difference is because I didn't center the filter exactly when doing the first measurement. Anyway, I take the average of the noise at the both sides and arrive here, and subtract the value at the peak, and this is then the noise at both sides of the filter. It is symmetricized like this. Then measured with the other settings, I get a similar table, but the peak value was different by, 3 dB about. But I take then to subtract 4.2 from all these values, and I get this table. And then finally I find that the floor is at minus 25.6, and I want it at minus 184.5, because I want to express the noise as the phase noise component referenced to the normal level of the carrier when this runs as an oscillator. And then I get this table. The result is the blue points in this diagram. At the peak I have minus 158.9, and it will stay there up until nearly 1 Hertz. At 3 Hertz it has dropped by 2 decibels only, and then it follows this curve, flattens out at minus 184.5 at about 1 kilohertz. And here is the noise floor which the oscillator approaches when I do the normal measurement, but it doesn't really reach it, and I think that is because of my system that isn't quite good enough for this. I have connected the noise head of my noise figure meter to the 2-channel receiver, and I have not changed anything on the receiver or in the settings on Linrad. And I have set the noise figure meter to 9.5 dB, means the excess noise here is 9.5 dB above room temperature. Then what I need in the S-meter graph is like this: minus 17.2 or 3 with a correlation advantage of 4.31 or so. That's the same as I found at 2 kilohertz. So that's the noise floor, the wide noise floor of my oscillator. An excess noise of 9.5 dB. So what I have found previously, the total noise minus 164.5, room temperature minus 174, means excess noise is the difference, that is 9.5 dB. So things seem to work perfectly okay.